3A, Describing Motion. 3.1, Introduction. Electrons moving through a tungsten light bulb flamete generate light. Photons. These photons reflect off the letters on this page as your eyes scan across them and strike sensitive cells in your eyes. The retinas in your eyes generate charges that rush along the optic nerves to relay images to your brain. Meanwhile, the sunlight streaming in through the window gradually changes direction throughout the day as the Earth spins around on its axis. The great wind and ocean current systems of the Earth spiral in response to the planet's rotation. Each night, the moon waxes or wanes during its monthly orbit of the Earth. The giant gaseous planets of our solar system revolve ponderously in their decades or even centuries-long orbits about the Sun. Distant galaxies retreat from us at hundreds and thousands of kilometers per second. The universe is full of motion. The study of motion is called mechanics. Mechanics includes all kinds of motion, from simple one-dimensional motion along a straight line to complex three-dimensional aviation and spaceflight. This chapter investigates motion, speed, and velocity, and acceleration. 3.2. What is motion? What is motion? Simply put, motion is a change of position. Scientists have divided mechanics into two branches: kinematics, to describe how objects move, and dynamics, to explain the causes of motion. Early Greek philosophers began their study of motion with the wrong question. They sought the causes of motion without understanding how things move in the first place. As a result, many of their ideas seem ridiculous to us today. How motion occurs, its description, must be known before its causes can be understood. 3.3 Mathematical representations of motion. If you were dropped into the middle of the ocean and you swam for an hour, how could you prove that you had changed position? Despite all your hard work, you might have swum in a circle. The only way to find out is to compare your first and last positions to a reference point, like an island. If your distance or direction from the island changed, then you could prove that you had moved. To represent motion along a straight line, you identify the object's position on a number line. The number line is a one-dimensional coordinate system. Each position is compared to a reference point called the origin. By convention, positions to the left of the origin are assigned negative values, and positions to the right are assigned positive values. For example, an object 4 men to the left of the origin has position of 4 men. An object 9 men to the right of the origin has position of 9 men. The axis of the number line may be oriented in any direction, including vertically. Up is usually considered positive, and down is usually considered negative. An object has moved if at one time its position is x1, and at another time its position is x2. Notice that each position is associated with a time. Position x1 occurs at time t1, and position x2 occurs at time t2. The object's position at each time can be represented by an ordered pair, written t1, x1, or t2, x2. Suppose you swim 21 lengths in a 50-meter pool. Because each length is 50 meters, the distance you swim is 21 x 50 meters, 1050 meters. But notice that after swimming 1050 mem, you end up only 50 meters from the starting point, at the opposite end of the pool. The distance or length of the path, SL, often differs from the net change in position. And this change in position between two distinct points is called displacement, d. In this example, S char 1050 m en, but d char 50 meters forward from the starting point. When a quantity contains only one piece of information, such as a distance of 1050 meters or a temperature of 50 degrees, it is a scalar quantity. A scalar value can be positive, negative, or zero. Scalars are symbolized by italicized letters, such as T for absolute temperature, when a quantity can be completely described only by stating both a magnitude and a direction, like 50 meters forward, which is two pieces of information. The quantity is called a vector. Vectors are represented by bold Roman characters, such as d for displacement. We will discuss vectors and their properties in more detail in Chapter 4. With motion along a straight line, the direction of a vector quantity is indicated by a positive or negative sign before the numerical magnitude of the vector. Forward motion is usually positive and backward motion is usually negative. Mathematical operations with vectors require special rules that you will learn in Chapter 4. To simplify vector operations in one-dimensional motion, we use a special notation that consists of the scalar symbol standing for the quantity with a subscript indicating the coordinate axis it is parallel to. For example, a displacement in the x direction is symbolized by dx. This notation represents only one-dimensional vectors, whereas the more general bold vector symbol can represent vectors in 1, 2, or 3 dimensions. The symbols dx and d are equivalent if d is parallel to the x-axis. In Figure 3.2, an object begins at position +1m at time t1. At time t2, it reaches Parseiferium to the right of its original position. Then it moves left until it reaches +2m at t3. The object's displacement, dx, for the interval t1 to t3 is its net change in position. That is, x increasing d1x plus d2x. dsc x2 dix1 plus x3 x2 rc x3 x1 dx arsh plus 3m plus 2m. dx hop plus 1 m, or 1 meter to the right of the original position. The object has actually traveled over a path from x1 to x2 and back to x3. The path distance is equal to the sum of the individual displacement magnitudes. Displacement magnitude is the absolute value of the difference of positions. This is true for linear motion in any number of dimensions. S fraction, absolute value. dx, absolute value. x2, 2, xi. The path distance for the object in Figure 3.2 is determined as follows. S shinser d sardes. Esir your pormium tronium sepsinium beamer your cherum sem ha shin timio 3 plus 2. Sisser shad subfaz. The object's displacement is +1 meter, but it traveled a total distance of 3.4 rate of motion speed. You probably saw ordered pairs like Tx in algebra. In that class, you plotted each pair as a point on a graph. You can also plot the Tx ordered pair on a graph called a position time graph. This type of graph shows much useful information in a simple form. For example, Figure 3.5a is the position time graph of a train on an east-west track between Ames and Marshalltown, Iowa. The graph shows several Tx ordered pairs. From looking at this graph, you might think that the train jumped from point to point, city to city. Obviously, this is impossible. The points are only the recorded positions of the train at certain times. If the train moved smoothly from point to point, you can draw lines connecting the points, as Figure 3.5b shows. From Figure 3.5c, you can find the displacement over a given time period. For example, suppose you want to know the displacement of the train from 0.60 h to 0.80 h. The graph shows that at t1 is 0.60 h, the train's is x1 you're 22 km east of its departure station. At t2 you're 0.80 h, its position is x2 38 km east, state center, the train's displacement. During that period is the change in x during the interval. That is dx or x2, x1, dx plus 38 km, plus 22 km, dex plus 16 km. At 0.80 h, the train is 16 kilometers farther east than it was at 0.60 h. What if the displacement is negative? For instance, what is the displacement of the train from T3, sir 170 h to T4, sire 2.0 h? At T3, x3 or 60 km east, Marshalltown. At T4, x4 or 48 km east, Lamoille. The displacement is as follows. T4, x3, dx, charge, plus 48 km, plus 60, das heißt. Dx is 12 km. In this answer, the negative displacement means that the train has moved backward west toward the origin. A position time graph also helps to determine the speed at which an object moves. The average speed, v bar, and of a train is the ratio of the distance traveled, x2, x1, over an interval of time, t2, t1. The absolute value sign is required because distance is always positive. If the train does not change its direction, its average speed is v bar x2, x1 over t2, t1. The symbol delta, Greek letter delta, conventionally means change in. So delta x means the change in position x, or x2, x1. On a position time graph, delta x is the difference between some position, x2, and the initial position, x1. The change in time, and delta t, or t2, t1, which is always positive, is the horizontal distance between the points on the timeline marking the beginning and the end of the time interval. In any linear graph, the change in height between 2 points, the rise, divided by the change in horizontal distance, the run between the points, is the slope of the line. In the position time graph, the slope of the graph is the ratio of the change in position and the change in time. The magnitude of the slope represents the average speed that a train travels between 2 points. The formula for average speed is v bar s over delta t, delta x over delta t. 3.5 Instantaneous Speed. As example 3 shows, the average speed changes depending on the interval chosen. The skier's speed increases as her position changes from the top of the hill to the bottom. Suppose you want to know her speed at any one moment, her instantaneous speed. For example, what is her speed at he moment she passes the third flag, 3:11's 30.0 m? The slope of the position time curve at that point is her speed. But how do you find a slope at one point on a nonlinear curve? One method to estimate the slope is to construct a tangent line segment at a single point on the curve and measure the tangent's slope. If you could view the point on the graphed curve with a zoom microscope, you would notice that as you increase the magnification power, the length of the curve segment visible in the eyepiece becomes shorter, and the curve appears to become straighter. At maximum magnification, the curve is indistinguishable from the straight line tangent at that point. To help you understand this concept, consider the curve of the Earth. Viewing it from the moon, you see that the limb of the Earth is clearly circular. But as you approach the Earth, the horizon becomes more sweeping and the curvature less distinct. By the time you touch down on land, the horizon appears to be flat. This small segment of the Earth's 4,000 kilometer circumference that you can see is essentially parallel to the tangent line at the point upon which you stand. In a similar way, you can estimate the skier's instantaneous speed at the third flag by zooming in on the curve around the flag. A very rough estimate for her speed at this point can be made by finding the skier's average speed for the entire run. This calculation was made in example 3-3. As depicted on the position time graph, figure 3-7a, your estimate would be the line connecting the top and the bottom points of the ski run. But the slope of this line is only roughly parallel to the tangent at the third flag, point D. To improve your estimate, try constructing a line between the endpoints of a shorter curve segment, for example, from point B to point E. This line is more nearly parallel to the curve at the third flag, so its slope provides a better estimate for the instantaneous speed at point D. However, you can improve the estimate even more. Figure 3-7c shows a line through points C and E that is nearly parallel to the curve at point D. Thus, its slope of 13.2 metres is a good estimate of the slope of the tangent, and therefore the instantaneous speed, at the third flag. In summary, you estimate the instantaneous speed at a given point by calculating the average speed of a small interval containing that point. The smaller the interval, the better the estimate. This is the graphical basis of differential calculus. The difference between average and instantaneous speed is important to automobile drivers, since the speed limit applies to instantaneous speed, not average speed. To maintain a particular speed on long trips, usually the speed limit, drivers often use cruise control. Although this device can maintain a certain average speed, it cannot guarantee that the automobile's instantaneous speed will always equal the speed for which it is set. Suppose, for instance, that a driver is traveling along a hilly road and the speed limit is 90 km/h, about 55 mph. The cruise control is set at that speed when the car begins to climb a hill. As the car climbs, it requires more fuel to maintain a speed of 90 km/h. When it reaches the top of the hill, the need for fuel abruptly decreases. If the cruise control cannot react quickly enough to reduce the fuel supply, the car speeds up and breaks the speed limit even though the cruise control was set at 90 km/h, figure 3.8. 3.6 velocity. You learned earlier that a distance such as 15 kilometers is a scalar because a single piece of information completely describes it. But a displacement such as 3 km west is a vector because it requires two pieces of information for its description. Like distance, a given speed such as 30 km/h is scalar. When a direction is included with the speed, for example, 10 ms due west, the quantity is a vector called velocity, v. To calculate average speed, you use the total distance traveled. To find the average velocity, v bar, you must find the ratio of the displacement, d, to the time interval, delta t, during which the displacement occurred, ve bar, d2, delta t. In one-dimensional motion, velocity is parallel to a coordinate axis, just like displacement, so it can be denoted by a scalar symbol and a subscript. For example, the velocity vector parallel to the y-axis is denoted vy. What is the difference between dach or delta x now in the average speed equation and d in the average vector velocity equation? The distance, delta x or s, is always positive. Displacement, either d or dx, may be positive or negative in one-dimensional motion and represents only the direct distance between two positions. The magnitudes of s and d will be equal if the object travels in only one direction during the interval delta t. Thus, a car traveling east on a straight road might have an average speed of 50 km/h and also a velocity of 50 km/h due east. However, if the moving object changes direction during the time interval, its speed no longer equals the magnitude of the average velocity over the time interval. Consider, for instance, the earlier example of a campsite and a picnic area across the lake. Suppose the family car travels along the 10-kilometer road at a speed of 50 km/h and took 12 minutes, or 0.2 h. Because the car's ultimate net change in position was only 2 kilometers and not 10 km. The average velocity vector is 10 km/h due north. A position time graph can show the velocity between positions. For example, turn to figure 3-5b on page 53 and find the points on the graph where the slope of the line changes dramatically. The value of the slope, including the sign, between each pair of these points equals the average velocity for that interval. You can calculate velocities for the train by finding the slope of each of these four intervals. 0h to 030h, average velocity, vx, share dx over delta t, share 14 km, 00 km, over 0.30 h, 0h, share plus 46.6 km h, 0.50 h, 0.80 h, average velocity, vx, bar dx, over delta t, 38 km, 15 km, over 0.80 h, 0.50 h, ashi plus 80 km h, 100 h to 144, average velocity, vx, sarsh dab, over delta t, 60 km, 38 km, over 1.44, 1.00 h, Gion plus 50 km h, 170 h to 20 h, average velocity in vex, farcar dx, over delta t, hersh 48 kilometers, 60 km, over 2 per 1.70 h, churn 40 km h. The average velocity for the last interval is negative because the train reverses direction. During the intervals 0.30, 50 h, 080 1.0h, and 1.44 170h, the train is stopped at a station, and the initial and final positions are unchanged, so the train's speed is 0. Figure 3.10 shows this data piosed on a velocity time graph. On such a graph, lines above the horizontal zero velocity line show positive velocity. Moving in the positive direction from the origin lines below this line are negative velocities, moving in the negative direction. 3.7 acceleration changing velocity. The last problem was simple because it assumed that the train's velocity was uniform during each interval, and that the velocity jumped instantly from one interval to the next. For instance, at 0.50 h, the train instantly gained 80 km/h. But you know from driving in a car that velocity changes frequently and smoothly, not in instantaneous jumps. This change in velocity with time is called acceleration A. Average acceleration, AAI bar, is the change velocity, delta V divided by the time interval, delta t, of the velocity change. Average acceleration, R, delta V over delta t. The quantity delta V is a difference vector. You will learn more about difference vectors in Chapter 4. When an acceleration occurs, the initial and final velocities can have different magnitudes, different directions, or both. However, in one-dimensional motion, the initial and velocities must be parallel to the line of motion, but maybe in opposite directions. Therefore, delta V can be expressed in scalar subscript notation as delta Vx var V2x, V1x. Recall that scalar subscript notation is reserved only for vectors that lie parallel to the coordinate axis along which position is measured. This statement means that the change in velocity in the x direction is the difference of the initial and final velocities in the x direction. The velocity difference points in the direction of the algebraic difference of the two velocities. Acceleration is a vector of magma-node delta, v, delta t, pointing in the same direction as delta v. In one-dimensional motion, AEI bar x may be positive, negative, or 0. A positive acceleration shows either an increase of speed in the positive directions or a decrease of speed in the negative direction. A negative acceleration shows a decrease of speed in the positive direction or an increase of speed in the negative direction. Zero acceleration means that velocity is constant. You can find acceleration from a velocity time graph. An object's average acceleration for an interval is the slope of the line joining the endpoints of the interval on the graph. Figure 3.11 is a hypothetical velocity time graph of a car on a straight street. Note that speed varies non-uniformly with time. The average acceleration between times t1 and t2 is the slope of the dashed line. The instantaneous acceleration at a point is the slope of the tangent to the velocity time curve at that point. Average acceleration does not have to equal the instantaneous acceleration from moment to moment. Do not confuse a velocity time curve with a position time curve. The slope of a position time curve is the acceleration. 3.8. Uniformly accelerated motion. In this example, the velocity time curve is a straight line, so its slope is constant. The car's acceleration must also be constant. Therefore, the average acceleration, a bar x, is the same as the instantaneous acceleration, ax. This kind of motion is called uniformly accelerated motion. We will study the significance of uniformly accelerated motion in the next section.